This is lesson 56, VHDL example 34, and in this example we'll write a VHDL program for the 4-bit multiplier that we designed in lesson 54. You remember in that lesson we saw that this circuit would do this binary multiplication here. And this is 4 copies of a component including an adder, a multiplexer, and a shifter. Now when you see something like this, it suggests that you might be able to use a for loop to sort of replicate this circuit, and then you might be able to do it for any number of bits. And in fact that works, so let's see how to do it. Here's A, we'll take the 4-bit case, 3 down to 0, B, 3 down to 0, and the product for two 4-bit numbers will be an 8-bit product in general, so this will be 7 down to 0. So here's the architecture for this multiplier. So to implement this circuit, we'll define 2 variables, PV and BP, corresponding to the P coming in and the BP coming in. We'll set the P's all to zeros, as we do here. We'll concatenate B with 4 leading zeros, as shown here. And then we'll go through this for loop 4 times, one for each of these blocks. First time through the loop, if I equals 0, we check to see if A sub 0 is equal to 1. If it is, then we want to add PV plus BP, which gets PV. And then we need to shift the BP 1 bit to the left, so BP gets BP 6 down to 0, concatenated with a 0. That shifts this 1 bit to the left. And then we go through the loop each time. Next time through the loop, if I equals 1, well, if AI equals 1, then we add. Otherwise, we just pass it through and don't add. But each time we do the shift. So this for loop will implement each of these 4 blocks, and then at the end the product is just PV. Note that we had to make PV and BP variables using the colon equals here, because every time through the for loop we need to update PV. We can't wait till the end of the process for those variables to be evaluated, so we must use variables there. Okay, here's the simulation. We take a binary counter for A, 0 to F, and we'll multiply it by F. So 0 times F is 0, 1 times F is F, 2 times 15 is 30, which is 1E, and so forth. 3 times F is 2D, so you can verify that this multiplication in fact works. Let's make a top-level design so that you can implement it on your FPGA board. We'll take our 4-bit multiplier, bring in the 8 switches. We'll multiply the top 4 switches by the bottom 4 switch settings, and we'll bring those out to the leftmost 2 7-segment displays, and then the product we will show as a 2-digit hex number on the 2 rightmost 7-segment displays. Well, the top-level design is straightforward. The top-level design will have the clock, the buttons, the switches, LDs, and then our A to G and AN for the 7-segment displays. We'll have the component Mult4A, the component X7 seg. We'll need 2 signals, X and P. X is the 15 down to 0 that will go into the X7 seg. P is the product 7 down to 0. And then we'll just wire it up. So the 2 leftmost switches will be the top 4 bits of X. That's the leftmost 7-segment display. The lower 4 switches will be X11 down to 8, and then the product will be the lower 8 bits. And we'll just do the 2-port maps. For the multiplier, we'll set A to the leftmost 4 switches, B to the rightmost 4 switches, P goes to the signal P, and X7 seg just gets wired up X to X, clock to M clock coming in, clear will be button 3, and the A to G's and AN and DP. So that should all work fine. Now you might wonder if we could use a multiplication sign to do multiplication like we did plus sign and minus sign for addition and subtraction. Well, the answer is that you can. Of course, we'll need our unsigned VHD program from our IEEE library here. So it's possible to just have A 4 bits, B 4 bits, and an 8-bit product. And in fact, you can just write P gets A times B. That seems pretty simple. And in fact, that works. You might wonder how VHDL implements that. Well, if you go look in the unsigned or arith program like we did for the addition and subtraction, you'll see what they do. Here they take a variable BA and PA. Now, the inputs are A and B, so they take A tick length, that's the length of A plus the length of B, minus 1. So in general, if these are 4 bits and 4 bits, then in general you'll have an 8-bit product, and that'll be 8 down to 0. So this will work for any length. They set the constant 1 to 1. They'll initialize PA to 0 using this others get set to 0. BA is just B, and then it's the two lengths, A plus B, so that'd be 8. And then they go through the loop. In this case, we'd go through 4 times, say, A tick length. That is the number of A's in the multiplier. So in our case, it would be 0 to 3. If AI equals 1, well, that's our little multiplexer. Here's the P is PA plus B, just like we did. And then you remember we shifted B 1 bit to the left. They just used the shift left function that we saw before. BA shifted 1 bit. So in fact, this is exactly the program that we just designed. And in fact, that's what they use. They'll return the product. So in fact, if you use the multiplication sign, it actually implements the combinational multiplier, exactly the one we designed. Of course, it will have every component that involves the multiplexer, the adder, and the shifter. The number of copies of those will be the number of bits in A. So if you multiply a 16-bit by a 16-bit to get a 32-bit product, it'll actually unwrap 16 of those. So you can see using the multiplication operator produces a lot of hardware.